All right, in today's lesson, we're going to learn how to graph a parent function. And when you hear the word parent function, parent just means it's the most simplest, basic form of that function's graph that we could actually look at. When I hear the word parent, it really means that there's no transformations involved. So we're not taking our graph, we're not changing it in terms of its size or shape. We're not moving it left, right, up, or down. We're not reflecting it. We're not stretching it. We're not compressing it. We're literally just looking at its basic form. So there's 6 different functions we're going to focus in on today. First one is a quadratic function. A quadratic function is something you probably were exposed to in intermediate algebra. What makes it a quadratic is when you see the exponent, the highest exponent in the function is 2. So a parent function for a quadratic is y equals x squared. And anytime I graph something for the first time, I always like to just make a quick table. X will be my input, Y will be my output. And to get a full range of what this graph's going to look like, I want to pick some values that are positive and negative. I'm just going to choose some basic ones like -2, -1, 0, 1, 2. All right, so I'm going to input -2 into this function. When I input it, -2 squared means -2 times -2, which gives me 4. For my output, when I plug -1 in, I get out 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. And then I can go ahead and plot these points. So we're going to go left 2, up 4. Left 1, up 1. 0, 0's at the origin. 1, 1, 2, 4. And of course, I could plot more points. And the more points I plot, the more detailed my graph's going to be. But we get a general understanding of what this shape's going to look like. And we have a U-shaped graph, and we call that U-shaped graph, if you recall from intermediate, a parabola. Now, to the right, we want to identify those key characteristics that we discussed in yesterday's lesson. So an x-intercept is where the graph crosses the x-axis. That's one time. We got to give both coordinates, 0, 0. Y-intercept is also at the origin, 0, 0. It's the only time it crosses the y-axis. Our domain from left to right is all x values. So in interval notation, that's -infinity to infinity. And for my range, we go bottom to top. There are no y values that are included in this function until I get to y is 0. And we're going to include 0, so it gets a bracket. And then literally it's everything above 0, so it's to infinity. Now I wrote maximum and minimum. That really should say relative max and min. We're going to focus more on relative max and mins versus absolute max and mins. So again, a relative max is where it changes from increasing to decreasing. And then for a minimum, it's just the opposite, where it changes from decreasing to increasing. So you can see in this graph, our graph from left to right is decreasing, and then it's changing to increasing. So we do have a relative minimum, and those coordinates of that point is 0, 0, and we have no relative maximum. There is no point where it's changing from increasing and then back down to decreasing. And then for intervals of increasing, this is always with respect to x. So from left to right, the first part of the graph, I'll kind of highlight it here. From left to right, it's going down. It's got a negative slope, so that's decreasing. And the x values in which it's decreasing from are -infinity to 0. And then it starts increasing from 0, and it keeps going to infinity. All right, and remember, for intervals, we always use parentheses. And the reason for that, again, is at 0, you can't tell me, is it increasing or decreasing there? It's not doing either. End behavior, let's describe what's happening at both ends of the graph. So on the left side, I'll say x goes to -infinity. For the right side, I'll say x approaches positive infinity. So starting with the left side, as I go left, what's happening to my function? Well, my function is going higher and higher and higher. So it's going towards positive infinity. And then on the right side, what's happening to my function? Well, it's going higher and higher and higher. So it's positive infinity again. And then is there a line of symmetry that I can draw in that will divide this into 2 symmetric parts? And in this rare occasion, we can. All right, if I draw a vertical line straight through the middle of the graph, we have 2 equal parts. So a vertical line is always x equals. And where's it going through on the x-axis? At 0. All right. Function number 2, we have a cubic function. So similar to what I did in the first one, I'm going to start by just making a quick table. X will be input, y will be my output. So I'm going to just pick nice, easy numbers again, some positive, some negative. We'll go -2 to 2. -2 cubed is -8. Again, that's -2 times -2 times -2. -1 cubed is -1. 0 cubed is 0. 1 cubed is 1. 2 cubed is 8. So we'll plot our points. We'll go left 2 down 8. Left 1 down 1. 0, 0, 1, 1, and then right 2 up 8. And based off the points that we plotted, we can see we get this type of function. All right, x-intercept 0, 0, y-intercept also 0, 0. Domain, left to right, all x values are included, so -infinity to infinity, same goes for the range. Relative max, relative min. All right, in this scenario, do we have any points that are changing from increasing to decreasing? And the answer is none. So none. Is there a point where it's changing from decreasing to increasing? No. So this has neither a relative max nor a relative min. And then from left to right, notice it's just increasing the entire time. It just keeps growing from left to right. So we're going to say the x values in which it's increasing are from when x is -infinity to when x is +infinity. We said it's never decreasing, so we'll write none. And then for our end behavior, as I move left, as I move right, describe what's happening to my function in terms of the y values. So as I go left, further I go left, notice my graph keeps going down, so -infinity. As I go right, it's getting higher and higher and higher, so +infinity. And then there is no line of symmetry for this one. Can't draw a vertical line anywhere to make the both sides mirror each other. All right, moving on to our third function. So absolute value function. All right, so how do we know this is an absolute value function? Well, notice the vertical bars. All right, and if you recall anything about absolute value, you probably remember the answer is always positive. Well, why is that? Absolute value really means the distance away from 0. So you can't have a negative distance. Distance is always a positive output value. So that's why. If I asked you from 0, what's the distance to 2? Well, it's +2. If I asked you what's the distance from 0 from -2, well, it's also +2. Distance is always positive. So when I make my table, I'm going to pick values again that are negative and positive, -2 to 2. Absolute value of -2 is 2. Absolute value of -1 is 1. 0, 1, 2. We can plot those points. We'll go left 2 up 2, left 1 up 1, 0, 0, 1, 1, 2, 2. And we get another shaped graph. This one's slightly different from our quadratic. Our quadratic, recall, was a U-shaped graph. This is more of a V-shaped graph. And for x-intercept, we have 0, 0, y-intercept 0, 0. Domain is going to be -infinity to infinity. Range is 0 to infinity. Relative max, none. Relative min, there is a point where the graph changes from decreasing to increasing. That's at 0, 0. And then interval of increasing, well, it's increasing from when x is 0, right? Increasing. From 0, we said, to infinity. And then it's decreasing from the left side. And that's from -infinity to 0. Again, those always get parentheses. End behavior as x goes to the left, as x goes to the right. What's happening to my function in terms of the y values? So left side, it's going up. +infinity. Right side, it's going up, +infinity. Line of symmetry, this one has one. I can draw it similar to like I had on our quadratic function. There is a vertical line I can draw straight through the middle of that graph, and both sides are going to mirror each other at x equals 0. All right, number 4, we have a square root function. So you should notice the square root symbol. All right, it's a radical symbol. Again, we'll make a table. All right, and I'm going to pick the same points, -2, -1, 0, 1, 2. Now, when I input the -2 into the square root of -2 we can't do. All right, we can't take the square root of a negative number because no number times itself is ever going to be back negative. The reason why the square root of 9 is 3 is because 3 times 3, or 3 times itself, gives me back that 9. We don't get that with a negative. All right, we can't take the square root of a negative because no number that's negative times itself will ever be back to negative. All right, so this will be undefined. Square root of 0 we can do. 0 times 0 is 0. Square root of 1 is 1. Square root of 2, I don't know off the top of my head, so let's choose a different value. I don't know the square root of 3, but I do know the square root of 4. Square root of 4 is 2. And the next square root I know is 9, so I'm going to choose square root of 9 is 3. So we have 0, 0, 1, 1, 4, 2, 9, 3. So if you look at this graph, notice it starts at a point and then goes forever in one direction. X-intercept, 0, 0. It's also the y-intercept. Domain is going to be from left to right. There's no x values that are included until I get to x is 0. It's going to get a bracket to infinity. Range from bottom to top. There's no y values included in this graph till I get to y is 0. And then it's everything higher than 0. So 0 to infinity. Relative max. Relative min. So is there a relative maximum? Does it go from increasing to decreasing? No, none. Relative minimum. Is there a point where it changes from decreasing to increasing? No. So no relative min. All right. I know you might be thinking that that 0.00 might be a minimum. It would be an absolute minimum, but it's not a relative min. By definition, a relative min has to go from decreasing to increasing, which we don't have. All right, intervals of increasing. It increases from when x is 0 to infinity. It was never decreasing, so we'll say none. End behavior as x goes to the left, as x goes to the right. Now, as I go to the left, notice there are no points to the left. So we're going to write does not exist. All right, and as I go to the right, my function just keeps growing, positive infinity. Line of symmetry, none. Can't draw a vertical line anywhere to make two equal parts. All right, we have two functions left. Our next function is a cube root function. Now, cube root looks similar to a square root. The only difference is that index number is no longer a 2 for a square root. It's a 3. All right, so we have a cube root of x. So again, we're just dealing with the parent functions. I'm going to pick some values that I know. This time, I'm not going to choose the cube root of -2 to start with because I don't know what the cube root of -2 is. I do know the cube root of -8. All right, so what number times itself 3 times gives me -8? Well, that's -2. -2 times -2 is 4, times -2 is -8. I also know the cube root of -1 is -1. -1 times itself 3 times is still -1. Cube root of 0 is 0, cube root of 1 is 1, cube root of 8 is 2. So I'm going to go left 8 down 2, left 1 down 1, 0, 0, 1, 1, and then we have right 8 up 2. So this is my cube root function. X-intercept is 0, 0, y-intercept 0, 0, domain -infinity to infinity, range -infinity to infinity, relative max, none, relative min, none. Interval of increasing. So from left to right, it continuously increases. So -infinity to infinity, nowhere is it decreasing. X goes to the left, X goes to the right. What's happening to our function? So left side, left side it keeps going down, -infinity. Right side it keeps growing up, positive infinity. And then there is no line of symmetry. All right, last one, greatest integer function. This is one you've probably never been exposed to before. Greatest integer simply means that we take any integer and round down to the nearest integer. So, give you an example. Greatest integer of 0 is 0. All right, 0 rounds down to 0. If I ask you what does 0.5 round down to as the nearest integer, that's 0. If I asked you what 0.99 rounds down to, well, that rounds down to 0. So anything smaller than 1 is going to round down to 0. But if I ask you what does 1 round down to, well, 1 rounds down to 1. And 1.6 rounds down to 1. And then 1.99 rounds down to 1. Anything smaller than 2 will round down to 1. But as soon as I hit 2, 2 rounds down to 2. All right, and what you get here is what's called a step function, where this process just keeps repeating. And I can go in both directions. Notice for each one of these steps, each step has a left point that's filled in and a right point that is open. Right? Sometimes we call a greatest integer function a step function for this reason. All right, and if you were wondering, like, where would I ever see this in the real world? Well, just the other day I had to go to FedEx to ship something. And based off of the weight of the thing that I was trying to ship, that determined how much the cost was going to be for me to ship it. So if it weighed between 1 and 3 pounds, I had to pay this amount. If it weighed between 5 and 7 pounds, I had to pay this amount, and so forth. That's kind of give you an idea of where the step function comes into play in the real world. All right, moving forward, this is going to be your practice on the last page. So I want you to work on this on your own. And then I have an answered key that's been attached to Google Classroom for you guys to check. All right, good luck.